It's nice to be back in Princeton. Today, I'm Dave Blei. I'll talk about the blessings of multiple causes. This is some new work that I started doing. It might have been causally related to leaving Princeton. I'm not really sure. But it started about 4 or 5 years ago. Okay, and please interrupt me during this talk. I hope we can have a fun discussion. So today's talk is going to be about causal inference from observational data, right? Which is trying to ask the question, if I observe a bunch of stuff in the world, how can I understand the world through that kind of data? This question is important in any field you can think of: genetics, economics, physics, medicine, finance, et cetera, et cetera. We observe something about the world, and we want to understand how the world works from that observation. And so what I want to talk about today is how to use probabilistic machine learning to help us do causal inference from observational data. Okay. I should mention this is joint work with my student Yixin Wang, and she deserves all the credit for this work. But if there's something you don't like about the work, that is my part of the work. All right. So the idea is called the deconfounder. And to explain it, we're going to talk about kind of a silly causal inference problem. Let's suppose you're a big-time movie producer, and you get a bunch of data about the cast of movies and how much money the movie makes. Okay, so you get a big data set, who's in the movie and how much the movie makes. And your goal as a big-time movie producer is to understand the causal effect of putting an actor in a movie. Okay, if I put Chris in a movie, how much money is that going to increase the revenue of the movie? It's causal because it's a question about an intervention. Causal inference is about interventions. What will the revenue be if I make a movie with Chris? Right? This is an intervention on the world. It's not how much money will this movie make that happened to have Chris in it. Okay, that's the key difference. Now, here's the data. This is real data where we have the cast of different movies. Here's Avatar, Titanic, The Avengers. Here's who's in those movies. And here's how much money the movie made. And the naive solution to this problem would, of course, be to fit a regression. Go from who's in the movie, a binary variable for each person in the movie, to how much money the movie made. Or even more naively, use deep learning to do the same thing. Right? Fit a neural network that goes from who's in the movie to how much money the movie makes. And in this little machine learning setup, actors are features, and revenue is the response variable that we're trying to model as a function of the features. The problem with this, why it's not causal, is that this estimates revenue as a function of which actors are cast. Okay, and so the difference between causal inference and predictive inference, or whatever you want to call it, is the tense of that verb. Revenue as a function of which actors are cast is different from the revenue as a function of which actors we cast. Okay, this standard machine learning setup doesn't necessarily provide causal inferences. Casting an actor is different from an actor being cast. And again, causal inference is about a prediction under intervention. Okay, so here's the problem with this setup. Anybody know this movie? Does anyone know what series of movies this movie's from? Okay, that's good. So this is a old James Bond movie. It's from Russia with Love. And I have a cheat sheet about James Bond for myself here. So for those of you that don't know, or to remind myself, what are James Bond movies? James Bond movies are movies about James Bond, who's a British spy. All right, here's James Bond here. It's Sean Connery, and he's a big star. Every James Bond movie casts the same set of actors. There's James Bond, Sean Connery, he's the star. But then there's the supporting cast. There's M, he's in charge of the British Secret Service. There's Q, he's the guy that gives James Bond his cool gadgets, like a fancy sports car or a pen that can release gas that kills somebody. And there's Miss Moneypenny, who's M's secretary, and they're in every James Bond movie too. Okay, so M, Q, and Miss Moneypenny, they appear in every James Bond movie, and by the way, they only appear in James Bond movies. Okay, so they're not in other movies too. But anytime we make a James Bond movie, we call them up. James Bond movies always do well at the box office. By the way, it seems like it's not a problem in this crowd, but if you know too much about James Bond, assume that there's only one James Bond, okay, and that it's Sean Connery. Okay, so James Bond movies have a star, they have a supporting cast, they're only in James Bond movies, and Bond movies always do well at the box office. Okay? And this captures the problem with doing this kind of standard predictive inference. If James Bondness is what's called an unobserved confounder in this data set. And it affects both the cast, which are the causes here, who's in the movie, and the revenue, the effect. All right? So you can see that if I know I'm making a James Bond movie, it's going to do well at the box office, right? So there's a connection between James Bond and revenue. But it also determines who I'm putting in the movie. I call Sean Connery, of course, but then I also have to call M, Q, and Miss Moneypenny. All right, and so if we don't encode this in the data, this is called an unobserved confounder. And it's the main issue that biases passive machine learning when used to form a prediction under intervention. Right? You can see what's going to happen. Because M only appears in James Bond movies, and James Bond movies always do well at the box office, we are going to misestimate M as being a very valuable actor. Okay? Some actors are overestimated and others are underestimated. And you can use the fanciest machine learning method you like. This is going to happen if you don't account for this kind of confounding. Okay, so what's the solution?
Question?
Yeah.
Is unobserved confounder the same as a latent variable?
No, it's not. I mean, it is a latent variable in that we don't observe it, and it's a variable. But it's a particular type of latent variable here. It's one that is lurking in our data. We don't get to see it, and it affects the causes and the revenue. Other latent variables, for example, that only affect the revenue, we're not talking about them now. Right? There might be other things that affect the revenue. Who knows what they are? The season, how much people like to watch movies. But if they don't also affect who I decide to put in the movie, they are not confounders. Yep. Okay, so what's the classical solution to doing causal inference from observational data? Well, it's to think, right? We want to think about what confounders might be lurking in our data, like James Bondness. We then measure those confounders, okay? So we go through our data and we write down what are the confounders for each data point. And then with our causes, the actors, the effect, the revenue, and the measured confounders, we can estimate causal effects using the techniques from the large literature on causal inference. Okay? But the problem is that this approach assumes that we have measured a sufficient set of confounders. We need to measure enough confounders to be able to do causal inference in a proper way. And whether or not we've done that is a famously untestable proposition. Okay? And so the classical solution rests on hope and makes us worry. And that's why I drew this person with worrying eyebrows, because you are always worried that you have missed some confounders. We're not going to totally absolve ourselves of that worry, but we're going to worry a little less at the end of this talk. Okay, but the point of this work is that this problem is not classical. There are many causes. In a classical causal inference setup, a bunch of people, some of them take Advil, some of them don't take Advil. You measure whether or not their headache went away, and you try to figure out whether or not Advil works. But the confounder might be that I take Advil when I know Advil works for me, and then I'm going to, of course, overestimate the effect of Advil. But Advil is just one cause, and in this problem, we call this a multiple causal problem. There's many causes, one per actor. Okay? And so we call that multiple causal inference. Each one of these variables represents one of the causes. And the point of this whole talk is that when I have a problem like this with multiple causes, I can construct a variable that contains some of the unobserved confounders. And then I can use that variable that I've constructed without actually observing the confounders to help debias the passive ML inference. Okay? And so here's the idea. What we're going to do is we're going to model the assigned causes, right? So we're going to model the actors using a probabilistic factor model. I'll talk a little bit later about what that is specifically, but think of something like a matrix factorization or a mixture model. These are examples that has a local latent variable. We then use that local latent variable to construct what we call a substitute confounder, and then we proceed with an inference, a causal inference, using our substitute confounder in place of the unobserved confounders. Okay? So model the who's in what movie, form a substitute confounder, and then perform causal inference. Okay, so in particular, the 3 steps are to find, fit, and check a factor model of the assigned causes, use the model to form substitute confounders for each individual, and then use those substitute confounders in a causal model of the outcome. And then going back to the James Bond example, you can kind of see in your mind how this might work. Right? If I had a bunch of data and I fit, if you're familiar with matrix factorization, I fit a matrix factorization on who's in what movie, I would uncover this kind of correlation structure between M, Q, Miss Moneypenny, and James Bond. Right? I could uncover this notion of James Bondness. It would be embedded in that factor model. Right? And so this is making a bit more precise that intuition. That if we can uncover that with a factor model, we can use what we uncovered to help us correct for confounders in downstream causal inferences. Okay, and it works. Right? So we do this, and the value of M and Q goes down, and the value of Sean Connery goes up. Okay, and so if you get this paper for review, Chris, you need no further evidence than this that it works. Okay, and we applied it to this goofy data set and found that people like Arnold Schwarzenegger and Robert De Niro and Brad Pitt are overestimated actors. They tend to appear in movies that are going to make a lot of money anyway, and so we overestimate their worth. Antonio Banderas and Cate Blanchett and Nick Cage and Owen Wilson are underestimated, and the algorithm most changes the value of people like Christopher Walken and Susan Sarandon and Ben Affleck and Stanley Tucci and Willem Dafoe, and in particular, it increases their value more than others. Okay, so this is not a totally credible analysis, but the point is that the inferences you make are different. Okay, and you can kind of squint. We'll have some more rigorous empirical studies later. You can squint and imagine that Arnold Schwarzenegger is going to appear in blockbuster movies anyway, and so we might overestimate his worth if we ran a regression on that data.
So
yeah.
Does that mean that he's overestimated? So if you were, that he appears only in blockbuster movies?
Yeah, so what it means that he's overestimated, what it means from the perspective of this talk is that, to be clear, I like Arnold Schwarzenegger. I think he's a great actor. Same with Robert De Niro and Brad Pitt. But what this means for this talk is this. If you run a regression on that data and you interpret the coefficient for Arnold Schwarzenegger as how much money is Arnold Schwarzenegger going to add to the revenue of this movie if I cast him in this, then that's going to be an overestimate relative to what this causal inference procedure tells you. Yeah, that's what it means. And it's not a serious analysis. It doesn't account for all kinds of things about like you can't just make a movie with every actor and then expect to make lots and lots of money, but that's what this model would tell you, that you just put everybody in it. So, take it with a grain of salt. But the point is that it changes our ideas of these of the value of these causes, of the effect of these causes, and I'll show you later on some simulation studies how it correctly can move towards more correct causal inferences. Yeah, Chris.
Maybe I didn't fully understand the details, but when you're doing causal inference, are you intervening only, let's say in this case, at the actor level?
Yes. Sorry. So
wouldn't you want to look? The intervention that I want to see is Arnold Schwarzenegger in a non-blockbuster film. But you can't do that, I guess.
Right. So what this setup is the following. You're a big-time movie producer, and what you get to do is create a cast of actors. Right? You can say who's in the movie, and you want to know how much money that movie's going to make. That's the whole story. And so here we're looking at individual actors, adding them in as how much that adds to the revenue. Yep. Yeah, Dan.
So I've forgotten the factor analysis, factor regression lingo, but how would this compare to having latent variables trying to explain the matrix of movies and actors, and have those same latent factors be a model for the revenue, and then trying to infer something from that regression?
Well, let me get back to that question, because I'll go into the details, and that question will be relevant when we talk about the details. Right? So in particular, well, yeah, let's get back to that question. Yeah. Okay, so what's the intuition? Right? Like I said, the intuition is that a certain type of confounder, like James Bondness, is called a multi-cause confounder. It's not a confounder that only affects one actor, but it affects multiple actors. And this induces a dependence among the causes. If you know that M is in the movie, then you can infer that Q is probably going to be in the movie too. Right? That's the dependence that this multi-cause confounder induces. And it's encoded in the data. So we can capture it with a factor model, with a latent variable model. Okay, so your question about latent variables versus unobserved confounders, we'll get to that too. The main assumption is that there are no unobserved single cause confounders. All right, so this is not magic. That if there's an unobserved confounder that only affects whether or not Sean Connery's in the movie and affects the revenue of the movie, then we cannot handle that confounder. That's an unobserved confounder that we can't handle. Okay? And of course, the movie example is just for fun, but you can imagine this multiple causal inference appears in a lot of different fields. How do genes affect a trait? There are many genes, and then there's a trait. How do the players affect a game? I might decide to put rich in my game, but how does that affect the points? How do the prices of items affect how much money is spent? If I raise some of the prices of some of the items in the supermarket, how does that affect the overall revenue of the supermarket? How do medicines affect lab measurements, right? If I am taking many, many different drugs, how does that affect my health outcomes? How do neurons affect limb movement? Neurons now are multiple causes, and some kind of aggregate behavior of the organism is the effect. Okay, although I hesitate to say that in front of Ken, who knows about neuroscience. But this is the idea, that these kind of multiple causal inference problems appear in many different observational settings that we might care about. Okay, so let's go into some more details. Our observed data set is A, Y. All right, A is, in this case, a binary vector of who's in the movie, and Y is how much money the movie made. And I have N movies. And we call A the assigned causes. Okay, that's who we decided to cast in the movie. Again, the outcome is Y. Our goal is to do causal inference. In Pearl's notation, we want to calculate the expectation of the revenue in a movie where I intervene on the cast, and I cast with little a. Good. Okay, so in classical causal inference, if there are unobserved confounders, then we have this problem. They call it the fundamental problem of causal inference sometimes, that the expectation of Y when I intervene on the cast is not equal to the expectation of Y conditional on the cast being little a. And this right-hand side I can calculate from my data, right, by subsetting all the movies that have the cast that I care about and taking an average of their revenue, but it does not equal what I'm after. Okay? So the procedure is to find, fit, and check a factor model of the movie casts, use it to form substitute multi-cause confounders, and then use those substitute confounders in a downstream causal inference. So I want to go over each of those steps, and then we'll talk about why it works. All right, so what's a factor model? What we mean by that is the following. It's a latent variable model of actors, not of actors and revenue, but just of the actors. And there's a per actor variable, beta j, that comes from some distribution. There's a per movie variable, zi, that comes from some distribution. And then whether or not actor j appears in movie I comes from some distribution that is conditional on the movie representation and the actor representation. Okay, so that's a factor model. Yeah, Sanjeev.
So movie, I mean, it's just a number, right? 1 to n.
That's right. So, but for actor, when I say actor, I mean column, and when I say movie, I mean row, and when I mean row, these are the units of analysis. I'm going to make a new movie, and I'm going to use these actors. So the columns are the causes, and the rows are the units.
But that last line distribution, does it depend on which movie it is? Or?
It sure does. Yeah, which movie it is ZI. Yeah.
What does that even mean? Movie is just a number.
Yeah, that's the row. So again, the way to read this is whether or not actor J appears in movie I comes from some distribution that depends on that movie I's representation and that actor J's representation. So think about, here are some examples. Mixture models, matrix factorization, deep generative models, topic models. These are all models that have this flavor, where there is a per column variable, a per row variable, and whether or not whatever I see in the cell of the matrix is about an interaction between those two variables.
Oh, I see. So movie is just a number. It's like some vector that describes what kind of movie.
It's a row. Yeah. This is a movie. This has some representation. Yeah,
but it has some representation on the.
Yep, in the latent space, exactly. Okay, and so these are all 3 books that if you open them to a random page, you're probably going to be looking at a factor model of some type. Okay, all kinds of models in machine learning satisfy this structure. Okay, so one example is Poisson factorization. Okay, this is basically a Bayesian version of non-negative matrix factorization. Let me put down my water. Where I've got actors and movies, overlapping plates. Each actor has a representation beta j, and beta j is basically a non-negative vector of length k. Each component has a gamma prior. Zi is a non-negative vector of length k. That's the representation of the movie. Each component has a gamma prior. And then whether or not actor j appears in movie I comes from a Poisson whose rate is the inner product of those 2 non-negative vectors. Okay, so if you're familiar with, well, there are a couple things to say about this. One, I know it's goofy to model binary data with a Poisson, but if you go through all of the terrible effort of truncating the Poisson at 1, you end up just doing a lot of math, and the results stay the same, first. 2, if you're familiar with non-negative matrix factorization with the original paper, this is basically a Bayesian version of that, where if you recall in that paper, there are 2 objective functions, the squared loss and what they call the KL loss. This is like the KL loss. That's really a Poisson likelihood. And so this is making that model more formal, or more Bayesian anyway. It's a nice model because so to be clear, it's a generative model of the assigned causes only. There's no outcome here. It can be approximated with large data sets using variational inference. That's what the Gopalan et al. Paper is about. And like I said, it's Bayesian NMF. Okay, so what do we do in the deconfounder? Consider the data set of casts, A1 through N. Approximate the posterior distribution, P of Z and beta given A. Right? I want to get my representations of actors in movies. And then I'm going to use that in the downstream causal inference. And this is to Dan's question. We only model the actors here. Okay, so I'm not considering the revenue when I'm fitting this latent variable. I'm just modeling the actors, how I cast movies. And intuitively, what we're doing is we're modeling the process by which the causes are assigned. Right? That's like the essence of that's a randomized trial is good because I have disconnected the outcome from how I assign treatment. And this is modeling whatever the treatment assignment is in my observational data. That's what we're doing here. Okay, we only model the actors. Okay, and so the next thing we do is check the factor model. Our goal in this work is for the local latent variable, by which I mean Zi, the variable local to each movie, is for the local latent variable to capture well the distribution of actors, to capture well how the actors are assigned to the movie. And so what we do to check the factor model is we estimate a local latent variable for each movie. All right, so here's a bunch of movies, and this is the posterior expectation of Zi. Right, so given the cast of Raiders of the Lost Ark, this is my understanding of its representation. And my hope is that when I take the inner product of this with the actor representations, I get a good probability of the actual cast of Raiders of the Lost Ark. Right? Blade Runner, 8 Mile, and so on. So this is the Zi's for each movie. Okay, I'm going to estimate it, and then I'm going to check how well Zi hat captures the true distribution of the actors. Okay? So in machine learning, this is just about checking the model. I want to check how well I can capture the cast of Unforgiven with this representation for the movie Unforgiven. And to do this, we appeal to the large literature on Bayesian model criticism. Rubin, Gelfand, Gelman, et cetera, who have nice work on how to check the fidelity of these Bayesian models. Okay, the point is that you can open those books and find a factor model, and so we can do this for many different factor models, and we can check each factor model, how well it captures the distribution of actors. Okay, so here I'm fitting, well, I'm not fitting these models. This is just a picture I made to represent lots of models. But here in this table, we're fitting these different factor models: probabilistic PCA, Poisson factorization, mixture models, deep exponential families. And each one gets a predictive score. This is our assessment of model checking. And you can see here, for example, that mixtures does not fit the data well. A simple clustering model is not a good model for the heterogeneity in actor casts. But these other models do well. And the deep exponential families does best. Okay, so that's the second stage. The last stage, then, is to use these ZIs as substitute confounders. So now I build an augmented data set where I take my data, I take my ZI hats that I fit from that factor model, and I attach them to the data. This is in place of, it's not in place of measuring confounders. This is to augment our measuring unobserved, our confounders. And I'm going to then use this data to do causal inference. Okay, I'm going to use these substitute confounders in a downstream causal inference. For example, if you're familiar with causal inference, I might fit a regression using both the cast and the substitute confounder. Here's that regression. And then I use adjustment to perform causal inference. Right? So once I have this regression fitted, this is a formula that lets me estimate y given do A. Okay? And this has different names. It's sometimes called the G formula. It's using the backdoor criterion and called backdoor adjustment in Perl's nomenclature. Yeah, Rich.
So the regression fitting step makes it look a little bit more like the model Dan was talking about, right? So here you're going to use both the assumed confounder and the inferred confounder and A to predict the revenue. So it seems like the question would be, I guess, rather than doing a separate fitting of the factor model first and then doing this, like integrating the two of them, how would that compare?
Right. So the problem, we'll get to that when we talk about the theory. I'll punt on this question yet again while I secretly think of an answer. But the difference, though, as you're pointing out, is that this looks like what Dan suggested, except that z is not a latent variable here. So we're taking z hat as observed, and then we are fitting this model. So what we're really doing here, and you could use, this is just one example, we are pretending that we have captured some confounding in this variable that we just constructed just by looking at the casts, and then we are using it in a downstream causal inference. If you want to use IPW or you want to use some other type of causal inference, you can at this stage. The point is to build this augmented data set, you check the factor model, and then you use it in a downstream causal inference. Okay, and so those are the three steps. Find, fit, and check a factor model. It could be a set of factor models, and you pick the one that's fitting the distribution the best. Use it to form a substitute confounder, and then use that substitute confounder in a downstream causal inference. Yeah?
So in sort of the more non-Bayesian terminology, basically what you're doing is you're trying to have a generated model for the data, and then, I mean, so that shows you which actors co-occur and all that.
Yes.
Just capturing that, and then using that, you are estimating the true.
Yeah, so I'm glad you asked that question. There's nothing specifically Bayesian about this.
You can do it with a neural net.
Right, so you want to capture the distribution of actors in a generative model, and that generative model should have a local latent variable. So this really needs to be a latent variable that you've got in play. But beta can be a point estimate, it can be whatever you want. And if you've captured a good distribution of actors, then your inference of this local latent variable can serve as a substitute for the multi-cause confounders. That's what the theory says. Dan?
Can we go back to the other slide where you had maybe two? Yeah. So I guess what's maybe strange from typical kind of factor analysis model would be that here you're not just having y depend on z hat or the z latents, but you're having it depend also on the latents generate A.
Yeah.
And so, of course, that's necessary if you want to do that do below. If I didn't have A there, there'd be no notion of doing A. Right on the bottom.
That's right. It's important.
So
Yep.
what? Now, to me, it seems like something like a magical balance. Why is it going to be that this regression is going
right? So first, to think about the answer to that question, imagine z hat was not fitted from A, but handed to you, right? I magically handed you the unobserved confounders. All right, this is just an execution of a standard causal inference pipeline in that case. You fit this conditional distribution, y given A and z, where z are your true unobserved confounder, sorry, they're observed confounders now, they're your confounders. And then this is adjustment for the confounders, right? This is like, with regression, this is what's done in a stack of papers a mile high. That's what it means when we say we correct for something. So is your question, why does z capture confounding? So if you agree that this is simply turning the causal crank, if I had observed confounders, the question you might ask is, well, but z comes from is some function of A. So why is this doing anything?
I don't come from a place of understanding causal inference that well, so I think it's probably a mixture of both. I don't
Okay.
really understand, but certainly, yeah, why should z capture?
Yeah, so that's what we'll get to next. Why does z capture? And that's also where we'll get to the question of why do we fit it just to the actors? But what this is an execution of the backdoor adjustment.
So I should take that on faith, you're saying?
Yeah, well, yeah, or it's in Perl, right? So basically, backdoor adjustment says expectation of y given do A equals expectation under the population distribution of z, the population distribution of the confounders of expectation of y given A and those confounders. And then this approximates that population distribution, this little empirical thing. Yeah, question?
I was just, I don't know if it's actually related at all, but I was just wondering if for example, Z is now taking into account what like James Bond-ness has to do with revenue, how does it really distinguish between M and Sean Connery? Like why if James Bond-ness is now causing the...
Good, yeah, let's think about that when we stare at this regression. So let's say Z captures James Bond-ness or not, and that's the only thing that confounds anything. So then eta is going to capture how much James Bond movies tend to make more than a typical movie. Okay? If I make a movie with M and Q and Miss Moneypenny and it's not a James Bond movie, what's going to happen to that movie? It's going to be a flop. And so eta captures how good James Bondness is. And so what that does is take some of the juice away from whether M is in the movie in understanding the revenue of that James Bond movie. When eta is big, then I'm going to now lower my estimate for M because I can explain the revenue of that James Bond movie without beta. Sean Connery is in lots of movies, and they're always hits. And so beta is going to be high for Sean Connery. Okay, so again, these are the 3 steps. And this is how I got this picture that's not credible at all. Don't make movies with this picture. Okay, so why does this work? The theory behind this says the following. If we fit a good factor model of the assigned causes, the actors, then its local latent variable, by which I mean the per movie latent variable, will contain multi-cause confounders, the same information as multi-cause confounders. Again, the main assumption is that there are no single cause confounders, or no unobserved single cause confounders. You can correct for them by adding them to this regression, of course, if you had them observed. Okay, so why does this work? So to see why this might work, I'm going to appeal to kind of an intuitive graphical model argument. And to be clear, this is a graphical model that represents joint probability distributions. It's not a causal graphical model. Okay, so suppose I find a good factor model. That means that I have found a model where the joint distribution of the causes is conditionally independent given some local latent variable z and the model parameters. Okay, in other words, I have this little graph. I've found a model that captures my true distribution of the assigned actors. Conditional on z, these are independent in that model, and it captures the true distribution. That's what that check is giving us. Okay? Now let's ask the question, can there be a multi-cause confounder lurking? Right? So the joint distribution of actors is embedded in a joint distribution of actors and revenue. And what does a multi-cause confounder look like? Well, it looks like a variable, w, that we don't observe, that affects multiple of these causes and affects the revenue y sitting in that joint distribution. But if I have found a model where conditional on z, these a's are independent, then this w cannot be any different cannot contain any information outside of Z. Because if it did, these A's would not be conditionally independent given Z, because there'd be a backdoor path in the non-causal sense. There would be an information flow up to W down to another A. Right? It would contradict the statement that the conditional distribution, that conditional on Z, the A's are independent. Again, let's think about James Bond. I feel like it's helpful, at least for me. Conditioned on James Bondness, whether or not M and Q are in the movie is independent. Right? It's going to be high for both of them, but they're independent. Okay? And so this contradicts the independent statement that we said held. A single cause confounder, if it only affects whether Sean Connery's in the movie and the revenue, does not violate that independence statement, right? In this little graph, this unobserved single cause confounder can still be lurking here, because even conditioned on Z, the A's are still independent of each other. Here, there is a dependence between them, even conditioned on Z, so it violates. So this is the argument for, if I find a Z that renders the A's conditionally independent, that Z captures unobserved multi-cause confounders. Now, it's a little more complicated to get all the way to Z capturing unobserved single-cause confounders, unobserved multi-cause confounders, sorry, because we need to also worry about a couple other types of variables. We need to worry about single-cause variables, like mediators and colliders, that are in between the actors and the cause and the revenue. And we need to worry about multi-cause mediators or colliders. Okay, so these are variables downstream from A that are between A and the revenue. The graphical model intuition does not help us here, but in the paper we prove that if we find a Z that renders the A's conditionally independent, it cannot pick up multi-cause mediators or colliders, and it also can't pick up any single-cause variables at all. Okay? So, of course, that means it can't pick up single-cause confounders, but it also can't pick up downstream single-cause mediators. And in causal inference, researchers in that field worry about mediators and colliders. These are downstream variables from the causes, because they also bias a causal effect. If you accidentally condition on a collider, then you bias your estimate of the causal effect from cause to effect, from A to Y. And so there's been some controversy around this paper centered around these results, but these results are correct. So this Z, we prove it in the paper, cannot pick up these variables, which green lights us to think of Z as a multi-cause confounder, or as a substitute for the multi-cause confounder. Okay, so the theorem, this is a cartoon of the theorem. Suppose I can capture the true distribution of causes with my factor model. In other words, I can write it as a marginal of under Z of conditionally independent causes. Then, with some other assumptions, the no unobserved single cause confounders, and that the causes pinpoint the substitute. In other words, I can estimate Z from A. I can estimate this latent variable from A with a deterministic function, and some other assumptions. Then I can identify the contrast between Y, where I intervene on A, and Y, where I intervene with A prime. Okay, so this is an identification theorem for this setup. Now, since we wrote this paper, there has been other progress on identification in the multi-cause setting. Some researchers have expanded the theory and made it stronger and made it more refined. I have some extra slides about that. If you want to ask me later, we can talk about that.
Can you explain that too?
What's that?
Explain number 2
This one?
on the previous slide.
Previous slide.
On the theorem.
Oh, on the theorem. Yeah. So number 2, think of it like, okay, so what number 2 says is this. I've got a factor model of the causes, and I'm holding it in my hand. I hold beta in my hand, all right? If you hand me A, you hand me a cast, I can tell you with precision what the value of the latent variable that generated that A is. Okay? That's what we mean by pinpoint. And let's again, it doesn't have to be Bayesian, but let's think about being Bayesian just for a second. If you have many, 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 many causes, a factor model is going to be able to pinpoint that, right? If you built a recommendation system and you watched a bazillion movies, the matrix factorization is going to be able to pinpoint your preferences according to that factor model. That's the idea. Notice that the reverse does not have to be deterministic here. In fact, it can't be. It won't be. So A is not a deterministic function of Z. There could be many, many trajectories of movie watching in this matrix factorization for a particular set of preferences, but given the trajectory of movie watching, I can get your preferences precisely. Yeah?
So then, is it important then that the regression you do after the fact is linear so that it cannot, say, compute F and ignore C, or not use C?
No, it's in fact, the linear regression was just an example. The model that works best, really, you can have, like Sanjeev mentioned, you could do, well, we'll go back to that for a second. You just need to model this. And so what we found worked best in our paper was to replace Z hat with a function of Z hat that actually calculated A hat. We replaced Z hat with the A hat that Z would give you, the expectation of A that Z would give you, which is a complicated, nonlinear, who knows what it is. It's still a separate variable from A. It's like the A it's like the cast that you think you would get. And that relates to instrumental variables, actually. It's like constructing an instrument. Yeah?
So your theorem is for fully general, or do you need this linear form somewhere, or your precise distributions?
So it's not fully general in that there are assumptions.
No, besides like some other, like the form of the distribution.
So this is a statement about, here we have a causal quantity on the left, and here we have an observational quantity on the right. And so it's a statement about how we can estimate this causal quantity with this observational quantity. That's the nature of an identification theorem. And so how you estimate this, that's downstream. Right? So it does not require that we use linear models anywhere, for example, here.
So it's fully general,
Subject to the assumptions. And the assumptions are going to be about the outcome model. But yes, that's right. It's not restricted to linear models. Yeah. Yeah.
So does 2 come with like an error tolerance? Because otherwise, wouldn't it be constraining a product distribution to have dimension 1, like effective dimension 1 less?
Yes.
In case it would like contradict itself. I guess because a product distribution can't have like support on 1 fewer dimensions.
Well, I don't know about the second part of what you said, but it does mean that, for example, K, the number of components, needs to be smaller, right, than the number of causes. I can't, if I had a 10,000 actors and a 10,000 dimension matrix factorization, I would have a problem with this. Yep. Yeah. So, the question is about how do we get to this pinpointing place? I mean, to be clear, this is a identification theorem, so there is always going to be a little bit of error here, right? But the point is you approach a delta as you get more and more causes. And we're thinking about cases like GWAS studies where there might be 10,000 or more causes, and you fit a factor model of like 5 or 10. Yep.
Maybe this is related, but so practically speaking, if you haven't considered the whole cast of actors, especially in James Bond, it might be that multiple movies have the same cast of actors. Is that so? So how would you just add actors until you could make that pinpoint? Did that question make sense?
I'm trying to understand the question.
So if Z is a movie and A are the actors.
A are the actors, Z is the local latent variable, the representation of the movie with those actors.
Right, okay, so.
If you had a lot of uncertainty about Z, then...
So if you have 2 data points that have the same set of actors, it's going to be the same movie.
Yeah, that's right. And that's fine.
Okay.
Yeah. It doesn't go the other way. That's the point. So A is not a deterministic function of Z. And we need that.
Okay.
All right. So this might help with some intuition. So this is not a free lunch. Okay, so it might sound like I'm trying to sell you free lunch, which makes no sense. But this is not a free lunch, right? So we only have observational data. We do not see these unobserved confounders. We are doing some analysis on these causes, and we're obtaining a variable that we're using as a substitute for unobserved confounders. So what do we pay to do that versus, say, measuring the confounders? First, the more information about the causes that's baked into the substitute confounder, that's the less information we have to infer the causal effect. All right? So if I can perfectly predict the cast, then there's no variance around that cast with which I can understand, how valuable it is to have Ken in the movie. Right? I need to have, sometimes Ken is in it, sometimes Ken can't make it, so that I can learn Ken's value, conditioned on everything else organizing themselves so that Ken would be in the movie if he could be. Right? So this has to do with the variance of the estimator. Okay? The variance of the estimator, it's unbiased, but the variance is going to grow if I have very, very strong sense of z as a function of a. In other words, a is a function of z. So here, this pinpoint is required for the identification theorem, but the other way around, we want that to be as uncertain as we can be, because that's the juice that we use to estimate the causal effect. It's the randomness after I've corrected for z. Again, think of z as imagine if z were observed. If I observed a confounder, once I condition on the confounder, I need Sean Connery to appear in other movies in order for me to understand his value. Okay. And so this tension affects the variance of the estimator. It also has effects on the theory. So this is the identification theory that has been progressing beyond this paper. Yeah, Rich.
Just trying to get a little intuition about this pinpointing. So imagine we have some movie like a French movie, some foreign artsy film, and we want to say, well, what would we get by adding Sean Connery or Arnold Schwarzenegger?
Right.
Okay, so we do a do on Arnold Schwarzenegger. How could we get a Z that would be a good explanation of the cast, given that Arnold Schwarzenegger and a bunch of French actors are?
This doesn't work for French movies. I should have said that in the beginning. It just is a fail. All right, let me think about your question. I should say, so we'll get to the empirical study. How do you go? You go for a while?
1:30 until 1:30.
1:30. Okay, great. Yeah. I was hoping I would have been happy with either answer. There are issues around what's known as overlap. And where, like, if there is a probability zero kind of possibility, then this theory doesn't work. We require overlap, that any actor is possible given any z. And that's a requirement of causal inference in general. If there's some kind of zero probability event, like Arnold Schwarzenegger appearing in a artsy French movie, then this doesn't hold in that case.
Even if it's low probability.
Well, right. So that's where we get to here. So overlap is like a yes or no thing. But if there's a very, very low probability chance, so we have theoretically satisfied overlap, any cast is possible, condition on any z, but that affects the variance of the estimator, right? If I need to make 10 million movies before I see these rare events, then it's hard for me to assess the causal effect of those rare events. To be clear, that's not a problem with this work. That's a problem in general with observational data and causal inference. If 1 out of a million people take the pill that think that it won't work for them, then that hurts how easy it is to assess the efficacy of the pill. Okay, so we ran lots of simulation studies. You can see them in the paper. This is a collage of the simulation studies. I'll just talk about one of them. Okay, or we can look at the collage. I'm hoping it has a causal effect on you, but we should talk seriously about one of them. Okay, so genome-wide association studies actually is the kind of the motivation behind it's how we got into this whole work, is by reading papers about GWAS, is a problem of multiple causal inference. How is genetic variation causally connected to some trait? For each individual, we observe a trait, and then many measurements on the genome, or SNPs. I'm not an expert in this, so if there are experts in the room, please correct me when I say things that don't make sense biologically. So multiple cause confounding is a problem, because non-causal SNPs, measurements on the genome, might be highly correlated to causal SNPs, and that misestimates causal effects, the same way that we misestimate M and Q. So we did a simulation. Here's the data. Our trait is going to be height, okay? And each unit here is an individual, and there are many, many SNPs for each individual, 100,000 SNPs. Okay, and SNPs have values 0, 1, or 2, whether or not you have 2 major alleles, the most popular one major, 1 minor, or 2 minor alleles. That's how they're measured often in this particular type of data. And so the first thing we did was we made a bunch of people on the computer using a model of SNPs, where we additionally put each person in some latent group. Okay? So the same way that we all have latent ancestry, we put each simulated person in some latent group CI. Okay? That we are going to not get to observe in the analysis. Then we generated the height of these people, where the true outcome is a trait, yi, drawn from this linear model, where you can see that the latent group Ci is playing a role in the height. Okay? So it's actually playing 2 roles. There's an intercept term, right? So people from Hungary might be very tall. And then there's also a noise term where the variance of that noise is also affected by the latent group. All right? So the variance depends on your latent group as well as the intercept. Here are the causes, the SNPs, and a coefficient for each SNP, and many of these coefficients are 0. Okay, so that's trying to simulate the real world where lots of the SNPs are non-causal. Notice the confounding. Ci, the latent group, affects both in some way what these SNPs are and affects the outcome. That's a confounder. And it's a multi-cause confounder because Ci affects many of these SNPs. Okay, so now we're going to play our game. First, we're going to fit many, many factor models. And notice that none of them is the true model. Right? We're just trying to model the distribution of A, P of A. Each one provides a different level of predictive performance. Okay, so here's probabilistic PCA, Poisson factorization. This is John Story's model, logistic factor analysis. Here's a mixture model, and here's the deep exponential family. As before, the mixture models perform poorly. The deep exponential family, which is a very flexible, deep learning inspired model, like a generalization of the sigmoid belief net, that performs well. These other models perform well too. We'll get to the end of the talk where I tell you that model checking is an inexact science, and something we need to do is make it more exact. But loosely, we say 0.1 is good enough, and below that is bad, but that needs to be made more rigorous. But anyway, we see the mixture model failing here. Now, what we're going to do is, by the way, we fit all these models with probabilistic programming, which was started by Dan Roy. So we used Edward. Now, what we're going to do is we are going to take each one of these models provides a substitute confounder, and we are going to use that substitute confounder in a downstream causal inference. Okay? Now here, we have the benefit of knowing the true causal effect of each SNP because we simulated the whole thing. So then we're going to measure the mean squared error between the estimated causal effect and the true causal effect. And of course, we have not used Ci in any of this analysis, the unobserved confounder. Okay, so I'll start at we're just going to look at the real valued outcome here. So with no control, if I don't acknowledge that there might be unobserved confounders and I just run the regression, this is my RMSE, 58. If I knew the confounders, if I knew Ci and I controlled for them, then it is less than half of that. Right? I get much better. But now let's look at what happens when I don't observe the confounder but use these factor models to assess how good my downstream causal estimates are. And you can see that we improve on 58 in all the models, 1. 2, the mixture model that fails also fails when I use those Z's, which I can do, as a substitute confounder. And we got signal for that here. And 3, the deep exponential family, that performed the best, and it also performs the best when I look at its when I assess its fit to the true distribution of A. And so the point here is that this is a simulation study. In reality, we get these numbers, how good our factor models are, and then we have to trust or not trust these downstream numbers. This shows us, at least anecdotally, that the predictive performance seems indicative of downstream performance of estimating the causal coefficients. Okay, and in GWAS studies, this idea of fitting a factor model and then correcting for it has been used in a lot of settings. It's something that is common in GWAS studies, and so one thing that this work does is provide some justification for doing that. Okay? As well as a method of assessing how well those studies are doing. Are they doing a good job because they are capturing true confounding structure, or because they are forming a substitute latent variable that contains the same information as the multi-cause confounders? Okay, so that's everything. In summary, well, it's not quite everything. How can we understand the world through observation? I showed you how to use probabilistic machine learning for doing causal inference. Again, model the assigned causes, use the factor model to form substitute confounders, and then use those substitute confounders in a downstream causal inference. I realize, Dan, I never answered your question. So why we don't use Y when we are fitting the factor model is that last part of the theory that says that we don't have colliders and mediators, variables that are downstream of the causes. If we used Y, we don't have those guarantees. And you can kind of see why. That if I include the outcome in modeling this factor model, I might accidentally pick up variables that are between the causes and the outcome. It also gives you the intuition for why we don't pick up those variables. It would be quite rare to magically find a variable that's correlated with Y and a cause if I don't use Y when fitting that factor model. Okay. If we find a good factor model, then its local latent variable will contain multi-cause confounders. There are assumptions and trade-offs. Okay, we increase the variance and so on. There's connections to lots of work in the research literature. And we're doing a lot of research on this right now, looking at structural equation models and the causal graphical view, looking at latent mediators and mechanisms. Could I find latent variables that are between the causes and the revenue? Using this in the context of networks where we are estimating social influence, and applying it to other settings like medicine, recommendation systems, sports analytics, neuroscience, and so on. Okay, so there's a lot. I told you about a lot, but this is a new idea, and there's a lot of open problems. The first one is that the field of model criticism needs attention. Okay, so we know that it's important that the true distribution of the assigned causes is captured by the factor model, but checking that is an inexact science. And there's some nice papers, but it needs some attention. Second, the deconfounder does not handle well, really at all, causally dependent causes. If your causes are in a time series, which many causal inference problems might have, then it's hard to find a factor model that will leave enough variance left over after you condition on its local latent variable to estimate causal effects. And so developing these ideas for time series models is an important open question. 3, theoretically, we don't understand this bias variance trade-off. Right? So the price of confounding bias and the finite sample properties. I showed you these identification theorem, but the finite sample properties are not understood. In other words, how much do we pay when we fit a factor model to estimate a substitute confounder? And that relates also to choosing the number of components in your factor model. Right? You want to somehow choose the minimum number of components that still fits the data well, but you want to minimize that number because the more components you choose, the more variance you're going to incur in your downstream causal estimate. But making that intuition rigorous is an open problem. And like I mentioned, we don't have a complete picture of causal identification. There's sort of a separate thread of research that came out of this, which is about how to do identification in multiple causal inference problems. And there's been some really interesting progress. Damour in 2019 and Koski, Imai, and Jiang in 2019 wrote some nice papers on refining the theory around identification here. Okay, so if you're interested, here's the paper. Thanks very much. Sanju.
It's referring to something that previously couldn't be done.
So why we called it the blessings of multiple causes? Because if you had the reason is, I mean, maybe it's just, too flowery, but the reason is this. With one cause, if I only had one actor in the world, we can't do anything. And so the point is that it's the multiplicity of causes that's giving us the lever that lets us estimate this substitute confounder.
No, but did people not know how to handle it, or there was no approach to handle it?
There was what?
Was there no approach to handle multiple causes? I'm trying to understand this.
Yeah, that's right. So this is a new perspective. Yeah. There was, of course, many people have been doing this, and these are all papers that were doing it in GWAS, but this perspective, the connection between this and causality, this is what's new. Yeah. Yeah.
I wonder what you can say if model the actor is not perfect. Say it's like very close in
Yeah.
KL or whatever. Is there any sense that you have that nearness in some metric? If it's nice for one as you like, that then the causal conclusions won't be too.
Yeah, no, that would be a great open question, right? So like there's a few things at play, right? There's the fidelity of the model, one. Two, there's the finiteness of the data, which induces variance. Even if I had the right model, the finite data induces more variance. And then three, there's the downstream causal inference. There's the outcome model and the adjustment. And so they're all interlocked. And so no, we don't know. And that's kind of what your question connects to my open question about model checking. Can I say something rigorous about like how close does this model need to be to P of A to get me within some ball around the true causal quantity? Yeah, that's a great question. Yeah.
When you talk about causal identification, do you have in mind any false discovery rates type of setup? I'm thinking about it, John Cunningham maximal entropy type of works. I want to make sure or like condense type of work. So if you're generating fake data with some covariate constraints and you're running your method on them, would you guarantee to have some identification?
So you're asking about false discovery, like if I'm doing GWAS and I'm gonna say this, and this have causal effect. Yeah, that's another open question here. So how to connect this to the nice literature on FDR and on multiple hypothesis testing, something we've thought a little bit about but haven't made any real progress on. It's a great question. So here, this work and the identification theorems are in some sense about complete interventions. Actually, so I'll get to the, there's been some other work on identification, and this is a little table of the landscape of some of these subsequent theorems that have been shown. And one of them, actually one that we show in our paper, is about subsets of causes. And so there, you can think of one cause as a subset of one, but then connecting that to FDR would be interesting. Yeah. Yeah.
Sorry, yeah, I was just also just to get some more intuition about how it works. I was just wondering, so if this would you sort of like explaining away, it would, for example, if in the previous example that if James Bondness now predicts a good part of the revenue, do I also need to see M in failed movies as well as Sean Connery in successful movies to allocate those, or do I need to see only one of the two? Like if I see M in unsuccessful movies, can I infer that Sean Connery is the cause of the success?
That will amplify it, but I think you just need to see Sean Connery in other successful movies without M.
And know that that would also give me the conclusion that M is less valuable.
Yeah, like I mean, I don't know if the data really says it this way, but the way that it would work would be that the model captures that, look, when M, Q, Miss Moneypenny, and Sean Connery are all in the movie together, that, let's say we had a binary factor model, that factor 42 is on, right? Then the regression would use factor 42 to explain the success of the James Bond movies. But the fact that Sean Connery's in these other movies and they are hits is going to push Sean Connery's beta higher. Yeah. Yeah.
To make a point estimate on disease, what is it a thing? Does it mean anything to say take samples of Z, push them through all the way to the end, and then get a distribution on your causal?
Love it. Okay, so here's some of my extra slides. One thing we can do is draw samples from Z, just like you just suggested, then draw samples of the outcome parameters conditioned on Z. In other words, replace Z hat with this sample of Z, and then just do the whole causal inference thing with this sample of Z. Then do it many times and get uncertainty bands. And, we just did it and haven't thought or proved anything about this idea yet, but it seems to work, right? It seems to give us, for example, in this identification theorem setup, there are some situations that are not identified, and it seems like, this is again very speculative, but it seems like we can kind of identify is the wrong word to use here, but we get evidence for when we are in an unidentified world. It seems that way, at least in this toy simulation, by doing exactly what you just suggested. And in general, we can get confidence intervals around these causal effects. This is a paper we did in medical informatics about this idea, and we can get confidence intervals around the causes by doing exactly this procedure. Yeah, but thinking more about it rigorously is something we haven't yet done. That's a great point.
Okay.
Good.
Thank you.
Thanks.